So in the last video, we discussed discrete Fourier series, which is basically how to apply the Fourier series, how to extend the Fourier series of the analog signals to a discrete periodic signal. So if an analog periodic signal is sampled, you get a discrete periodic signal, and then to analyze the frequency contents of analog periodic signal, you use Fourier series, and we extended the Fourier series for the discrete periodic signal, and we called it discrete Fourier series. So in this topic, in this video, we're gonna discuss the topic of discrete Fourier transform. And what is discrete? What is the basic premises of discrete Fourier transform? So discrete Fourier series is applied only on periodic signal, discrete periodic signal. Now, most of the time, our signals, the one that we are analyzing the frequency contents of, they are not periodic signals. For example, I'm talking to you right now. If you want to see what are the frequency contents of my speech or my voice, you can grab a few second sample of my voice, and then you can analyze the frequency contents from that sample. Now remember, voice frequency generally goes from 300 hertz to 3.3 kilohertz or something like that. Irrespective, you have a 2-hour long speech, or you have a 10-minute, or you have a 1 minute, or you have a 10-second. The frequency contents are still going to be between that range. So practically, we grab some time limited signal to observe the frequency content of that signal. Now remember, this time limited signal is not a periodic signal. So it's not a periodic signal. So discrete, how we apply discrete Fourier series, that's when the discrete Fourier transform comes into act. So we're going to discuss the discrete Fourier transform, but before we do that, I have not discussed example 4.1 with you, which is based on discrete Fourier series. So let's go ahead and quickly first discuss example 4.1 and see how did we calculate the components dk, the frequency component dk from for the discrete Fourier series for this example. So in this example, as you can see, I have a signal 5 sine 2 pi t. 2 pi is omega is 2 pi f, so f is 1 hertz in this problem, and signal is sampled at 4 hertz. That means it is sampled greater than the rate of Nyquist. Nyquist rate for this will be 2 hertz. So it is twice the rate of Nyquist, hence it is oversampled. Hence you should be able to recover the original signal from the samples if you use a practical low pass filter. So here are the samples. So this is my signal. It has a frequency of 1 hertz. That means your time period of the signal is also 1 right here, and it is sampled at 4 hertz. That means your sampling time is going to be 1/4, which is quarter of a second. Hence there will be 4 samples in one cycle. As you can see, sample number 1, which is x0, x1, x2, and x3. Now remember, from this point the new cycle is going to start. So this sample is not part of one period. We have 4 samples, x0, x1, x2, x3, but x5 or x4 is not going to be part of the period. That's the part of the next cycle. Alright, so we have 4 samples. The values, as you can see, x0 is 0, x1 is 5, x2 is 0, and x3 is -5, and those values are given over here. So I calculated those values, of course, in MATLAB. Okay, so that means we will have 4 spectral contents as well, corresponding to 4 samples. So my harmonic number k is 0, 1, 2, 3. 0 is DC, 1 is fundamental, 2 and 3, of course. Frequency resolution is sampling frequency divided by number of samples in one cycle, so it's going to be 1 hertz. That means in the frequency domain, in 4 hertz, my sampling frequency 4 hertz, I will have 4 spectral contents, and those spectral content are going to repeat themselves in each cycle. So I take dk, the equation of dk, of course, and this is the expression 1/4, of course, 1/n, 1/4, and then n goes from 0 to 3. We have 4 samples. and then of course k is also going to go from 0 to 3, which is right here. So d naught, that is the average value, is 1 over 4 1 over n x0 times e to the power negative j 2 pi k. Remember, n is 0 and k is 0 both for d0. 0 means k is 0. So for all of this summation values, k is going to be 0. Therefore e to the power negative j 2 pi k n, when k is 0 for d0, that's going to be 1. So all you have is a summation of x0 plus x1 plus x2 plus x3 divided by 4 for d0, which is going to come out to be 0, of course. 0 plus 5 plus 0 plus negative 5. d1, again 1 over 4 x0 e to the power, n is 0, of course. For the first one n is 0, so for the first x0, this exponent term is always going to be 1. Now k is 1 over here, right? So we put k is equal to 1 in the equation, and then n is changing from 0 to 3. So for n is equal to 0, this will be 1. For n is equal to 1, that's going to be e to the power negative j 2 pi over 4. So j pi over 2. 2 pi over 4 is pi over 2. And likewise, n is equal to 2. K is still 1. We have a negative j pi and a negative j 3 pi over 2. Alright, when we go to the next one, n is going to come out to be negative j 2.5 when you calculate it. When you go to the next one, d2, now k is equal to 2. So you're going to go ahead and put k is equal to 2 over here, and then do the summation from n is equal to 0 to 3 for that. And you're going to get x0 plus x1 e to the power negative j and this and that. And it's going to come out to be 0. And the last component, oh, I did not fix it. This has to be 3. This is 3. So d3, then it is going to be basically e to the power negative j 3 pi by 2 negative 3 and then this, and your result is going to come out to be j 2.5. So observe that this and this are complex conjugate of each other, right? And then this and this are same. So when you take the magnitude of that, of course it's going to be 0. Magnitude of negative j 2.5 is 2.5, 0, and then magnitude of j 2.5 is 2.5. Okay, so when you go ahead and plot this versus k, harmonic number, and versus frequency. Now remember, we discussed that how to go from k to the frequency. Each value of the k scale is going to be multiplied. Let's say 0 is here, it's going to be multiplied by f0. So it's going to be 0 f0, which is 0. It's going to be 1 f0. It's going to be 2 f0, 3 f0, 4 f0, so on and so forth, right? So your one cycle is this from here to here. This is your fs, sampling frequency. Remember, sampling frequency is n times f0, so 4 times f0 from here to here. Of course, sorry, 4 times f0 over here. Why I made a mistake over here. Let me go back real quick and clean that up. This is part of the cycle. So that's gonna be from grab my pencil again. That's gonna be from here to here. Sorry, 4f0. This will be the sampling time over here. So you have the first component, which is the DC value, which is 0. You have the fundamental component, the value of which is 2.5, magnitude of which is 2.5. Remember, each one has a phase as well. I'm just plotting the magnitude right now. And the second harmonic with the value 0, and the third harmonic with the value 2.5 again. And from here, the next cycle is going to start, right? So Fs has 4 components, 4 times f0, of course, total Fs, frequency, sampling frequency. And observe, important thing over here is, remember the frequency of the signal was 1 Hertz. So observe where you have the spike. You have the spike at 1 Hertz. And Fs by 2 is 2. This is Fs by 2. Of course, this is Fs, remember. Remember, you can have all the frequency contents from 0 to the folding frequency. And in this case, you have only one frequency in the signal, which is 1 Hertz. And after fs by 2, from fs by 2 to fs, you just have the mirror image of whatever you have from 0 to fs by 2. So you have the mirror image of this, which is this. But the frequency contents of the signal, all the frequency contents, you must get the information for all the frequency contents from 0 to fs by 2, or you will get all the information from 0 to fs by 2. So there is only one frequency in the signal, which is 1 Hertz. Make sure 3 Hertz is not the frequency of the signal, because again it is outside fs by 2. So you will get all the information from 0 to fs by 2. Although when we are taking the Fourier series, you go from 0 to fs. But remember, you don't have to, from fs by 2 to fs is just a mirror image of 0 to fs by 2. So all the frequency information is from 0 to fs by 2. And in this case, it's only one frequency component, which is 1 Hertz. Okay, so let's move on to discrete Fourier transform. So as I explained at the beginning of the lecture, if you have a voice signal or any signal that is not periodic in nature, how do you calculate the frequency contents of that? Very easy. What you have to do is, let me look at the picture first. All right, so let's say this is your signal, right? And you are interested in only a part of the signal to calculate the frequency content, and this is the part of the signal T0. So you are calling it the time that you are extracting from the signal, that time is T0. So what you do is you extract that time, you sample it with some sampling frequency, and then you repeat that, or you repeat this pattern first and then sample the signal with some sampling frequency. It's the same thing, right? For either you first sample it and then repeat the samples for to create a periodic signal, or you first create the periodic signal and then repeat the cycle. So basically what we are doing is we are making a periodic discrete signal out of the signal that you want to analyze for the frequency contents. So your one cycle is still the same, what you want to analyze, right? And that's all you want, right? You only need one cycle to get the frequency contents. So even though this is the extension of what you want to analyze, but it is the periodic extension. And when you have the periodic extension, that is the periodic discrete series, all you need is one cycle to analyze the frequency content, and that's what we are going to do. We are going to sample the signal with some sampling frequency. Practically, of course, it has to be greater than Nyquist rate. And then we will, once we sample the signal, we will have n samples in one period, and those n samples are going to give us the information about the frequency contents, n frequency contents in the frequency domain. And of course, those frequency contents will, all the frequency contents, all the frequency information will be from 0 to the folding frequency, 0 to n by 2, cap n by 2, and from cap n by 2 to n is just the mirror image of the first half of the spectrum. So that's what Fourier transform is, as simple as that. As far as formula is concerned, you take the Fourier series formula and you basically multiply the Fourier series by cap n. Where is it? Right here. You take the Fourier series dk and you multiply dk by cap n. So basically you are scaling the Fourier series. Remember, dk is 1 over n times whatever you see over here, this, right? So basically you're cancelling this n. When you multiply dk by n, this n will be cancelled out. So all you have is summation of samples for one cycle over one cycle, 0 to n by minus 1, e to the power negative j 2 pi k n over cap n. All right. One thing that we're going to discuss in the next topic, which is the window functions, is when you take, when you extract a portion of the time domain signal that you're interested in. If you are extracting the signal such that your end values are not 0 or not very close to 0, then what happens is you will get discontinuity in the repeated pattern. Give you an example. So let's say you have a sinusoidal signal and you wanna extract some some time of this sinusoidal signal. Let's say I start from here at 0, but I just go up to this point, right? Instead of going to the 0, I just went up to this point. So what's going to happen is when I will repeat this, I want to go to this point, and then I'm going to, next cycle I will drop down to 0 before my next repetition will start, and then I drop down to 0. So this creates discontinuity in the periodic pattern. Anytime you have two values at one point, so it has a high value, and at the same time the next cycle is going to start and it will drop down to 0. That's the discontinuity. Now if we clean cut a signal, that is the end values are 0, so when the next period is going to start, it will start at 0. You have a continuous signal. But if you have a discontinuity in the signal, that gives rise to a lot of harmonics, what we call harmonic noise. And then those harmonics basically they appear at usually or they mess with the signal frequency spectrum, and you can see those harmonics. So we're going to use the window functions in the next topic to kind of smooth out those harmonics, but that's just a tangent for the next topic. It doesn't relate to this topic right now. Okay, so when we have this equation of Fourier transform, then generally what we do, we use W's of n, and we we assign it e to the power negative j 2 pi over cap n. 2 pi over cap n, because cap n is constant, of course. If you have 10 samples, cap n will be 10. So that's Euler's identity, cosine 2 pi over n minus j sine 2 pi on, and you can calculate a value from this, right? And that value you can substitute here and take the power k times n for that value. And that's just to make basically expansion a little easy when you're solving a problem. So this W's of n is called twiddle factor. I don't know where this name this name come from, but in your book they're calling it twiddle factor. I'm just going to go with that. So this is your discrete Fourier transform of the signal, which is the same as discrete Fourier series multiplied by cap of n. In Octave, MATLAB, you have the function FFT, fast Fourier transform, which we're going to discuss the last topic of this chapter. You can use FFT function to calculate the discrete Fourier transform. Now, from discrete Fourier transform, which will give you x of k, which are the frequency contents or spectral contents of the signal. From those spectral contents of the signal, you can go back and find the samples from which the spectral contents were calculated using inverse discrete Fourier transform. And the formula is given over here. Not going to go in the detail. You have seen this formula is the same. Pretty much the only difference is you are, instead of using negative value, you are using positive value of j2 pi k n over n, and instead of x of n, you're using x of k, and k is going from 0 to n minus 1 instead of n going from 0 to n minus 1, and the result is not x of k, the result is sample x of n. Let's see, there's an example. I have 4 samples from some speech signal, and I'm using these 4 samples to calculate the discrete Fourier transform of the signal. Okay, so my sampling time is my sampling frequency is 8 kilohertz, so my sampling time is 1 over fs, 125 microsecond. That means the time period in the time domain is going to be n times ts. Ts, remember, is the sampling time, so the time difference between each of the consecutive samples is ts. So my time period, my number of samples are 4, which are given. My time period is 4 times ts, 500. My frequency resolution in the frequency domain is fs over n, 2 kilohertz, and of course the length of one cycle in the frequency domain is equal to fs. So fs is 8 kilohertz. I have 4 sample. That means frequency resolution is 2 kilohertz per sample. And the twiddle factor I calculated, and it came out to be negative j1. So I'm going to use the formula of DFT like we discussed in example 4.1. Pretty much the same, except of course we are dividing that by, we are multiplying the d of k by n, cap n. So the formula is here. I put the expansion of that as well. n goes from 0 to 3, to real factor n to the power k. So x of 0, for the first one always n will be 0, so anything power 0 is 1, so for this it's going to be 1. The second one, n is equal to 1, so total factor to the power k. For the third one, n is equal to 2, total factor power 2k, and for x of 3, n is 3, so total factor to the power 3k. So I will use this to calculate my x of k, my frequency contents for k is equal to 0, 1, 2, and 3. And when I do that, I will just change the value of k over here, and then I will calculate x of 0, x of 1, and all those, and you will see that you're going to get this result. Now, since of course you see that x of k is a complex quantity, and when it is complex quantity, you have amplitude associated with that and phase associated with that. So you have amplitude and phase spectrum. You have one spectrum for amplitude, one spectrum for phase. And how we calculate it for the amplitude spectrum? Basically, you calculate the magnitude of x of k and you divide that by n. So remember, you're dividing it by n, so you're going back to Fourier series dk, because to get x of k, you multiplied the Fourier series by n. So to calculate the amplitude of the coefficients, you take x of k and you divide it by n. You take the magnitude of x of k. So magnitude of any complex number is calculated as real part square plus imaginary part square root of that. So you do that. This is called the double-sided spectrum, and you can also do the single-sided spectrum, and that is from 0 to n by 2. Instead of 0 to going from 0 to n minus 1, you go from 0 to n by 2. So these are the formulas for single-sided spectrum. For DC component, it is the same as A of k, and for the harmonics and fundamental, you just double up each of the components. So basically, from the folding frequency, you fold from 0 to fs, from fs by 2 to fs, you fold on top of 0 to fs by 2. So each component that will be aligned, though that component, the magnitude of that component is going to be doubled, because you're adding the two similar components, and that's why you see 2 of n. So that's the single-sided amplitude spectrum. And the phase spectrum you calculate for any complex number. Phase is calculated as arctan of imaginary over real, and that's how you calculate the phase spectrum as well. In MATLAB, you have function absolute ABS to calculate the magnitude of any complex number, and then you have a function angle to calculate the phase of any complex number in radians. So if you want to convert into degrees, multiply by 180 divided by pi. You can also calculate the power associated with each harmonic using power spectrum, and the formula is given over here. You can read the formula, I don't have to go over the formula, but power spectrum is going to be used to calculate the power associated with each harmonic, fundamental, and DC component. There is an example. You can look over the example, go over it. Pretty self-explanatory example, and nothing really complicated. So look at that, the plot of the example. And there is another example. So again, go over that example, and then pretty easy to understand. One thing actually I do want to discuss in this example that I think I'm explaining it over here as well. Observe this x of t. Observe what frequencies do you have. So this is a compound signal. It's two sinusoidal multiplied by each other. Anytime you have a compound signal, two sinusoidal multiplied by each other, you can always use trigonometric identity, cosine a plus b and cosine a minus b, or sine a plus b and sine a minus b, to find out what are the frequencies involved for each of the cosine component here. So let's say 2 cosine 3000 pi t, sine 7000 pi t, right? So sine a plus b is sine a, if you remember, sine a cosine b plus cosine a sine b, and sine a minus b is sine a cosine b minus cosine a sine b, right? So if you add these two together, the second component is going to be cancelled out, and you will have 2 sine a cosine b. Okay, so look at that, 2 sine A, if I call this A, 7000 pi t, cosine B, right? And what is that? Sine A plus B, which would be sine 3000 pi t plus 7000 pi t, or 7000 pi t plus 3000 pi t, 10,000 pi t, sine A minus B. So one component has 10,000 pi t, that is the frequency of that component is 5000 hertz, and the other component is 7000 minus 3000, 4000 pi t. The component value, the frequency value is what? 2000 hertz. So from this I have 5000 hertz frequency, and from this I have 2000 hertz frequency. And the second part of this signal is 5 sine 10,000 pi t. What is the frequency from this component? Again, 5000. That means in your spectrum you are expecting that you have components at 5000, this component and this component, and you have one component at 2000. So when you so this is what you're expecting when you draw the spectrum, right? So when you draw the spectrum and you are taking about 100 samples from this signal, sampling at 15 kilohertz oversampled, and then when you plot the spectrum, and of course remember, when you're taking 100 samples, you're not going to use your hand to calculate DFT and all those things. You're just going to use MATLAB and FFT function. So when you use MATLAB, first grab the 100 samples, use MATLAB FFT function, calculate the Fourier transform, and then calculate the amplitude spectrum using the magnitude of Fourier transform divided by 100, total number of component, and then plot them. So observe what do you get? You got one high peak at 5000 hertz right here, and you got one higher peak, higher than other, at 2000 hertz, and that's what you are expecting. And again, you have to go from 0 to fs by 2, so 0 to 7.5 kilohertz. That will be all of your frequencies. From 7.5 kilohertz to 15 kilohertz is just going to be the mirror image of this, as you can see, right? So you have one 5000, or one component, actually two components, but both the frequencies are 5000 hertz. You have a frequency 5000 hertz, and you have a frequency 2 kilohertz, 2000 hertz. Look at all these. This is what I was talking about, the spectral leakage or the noise if your signal is not properly cut, such that if you have discontinuity when you repeat the signal, that's what's going to happen. That's the harmonics. It's called spectral leakage, that we are going to discuss in the next topic, and that will be for the next week.